All right. So today we're discussing extreme values, concavity and convexity, and sketching graphs. So let's get into it. Much better. So to begin with, we have a pen that doesn't want to work. Must be Thursday or something like that. Much better. And we have this function f of x is equal to x fifth plus x squared plus 2x, if I remember correctly. Yes. On the interval AB. Okay, so we want to find if this thing here has local extreme values. So first of all, we are calculating the first derivative. That's 5x fourth plus 3x squared plus 2. And the second derivative is 20x cubed plus 6x. So first of all, we look for local extreme values. First thing we're going to do, and we're going to solve this using this change of variable. We have 5t squared plus 3t plus 2 equals 0. So t here is minus 3 plus minus the square root of 9 minus 40 divided by 10. So possible relative extremes don't happen here, which is good. Secondly, we're going to study increasing and decreasing of the function. We observe the following. This is always positive. This is positive. This is positive. This is positive. So the function always grows. So the absolute minimum of f of x, positive 2, it's 2, and it's reached when f equals 0, right? No, the absolute, the negative is this. And here, actually, this is true. I made a small mistake here. I was analyzing the first derivative instead of the function. Does this have vertical asymptotes? No, it doesn't, right? Okay. So from here, we have that in this interval, the maximum value of the function is f of b. And the minimum doesn't exist because the interval doesn't contain a, but the infimum, or the theoretical lowest value, is f of a. And yeah, here you can replace f of b and f of a in this polynomial here, and you will get the answer. So strategy here, we search for relative maximums and minimums, don't find them, look for some properties of the function that allow us to determine where the function grows and where the function decreases. Here, this changes sign at 0, so this function is something like this. So yeah, it makes sense that we only found maximum and infimum here, because the function is like an S in some sense. Now, moving on, let's do a more concrete example of this. And I'm going to show you number 11. And the interval is 0, 1. So first of all, we notice that f of 1 and f of x tends to minus infinity when x is smaller than 1. So we have an asymptote. Looking at the other extreme on the interval, f of 0 is -1. So we don't have a problem here. Now, I could draw this function. It looks something like this. And here we already have all the information we need. We know that the maximum in this interval would be f of 0. Now, none of them are included, so we cannot actually talk about maximums and minimums, but supremum and infimum of the function. However, let's see how the book phrases this. I forgot a detail and nobody told me. Here, that thing happens, and so we have a local maximum. It's a local maximum, right? Yeah. And obviously a local minimum in 1. This is the local maximum, this is the local minimum. Now, questions. Where can you find the recordings? In Canvas, there is a page called Where to Find the Tutorials, and you can follow the link there. Good. Now this looks barely visible, but my pen just died, so I have picked up another, so we can move on. All right. Number 19, does this function have local extreme values? If they are they absolute? Are they relative? Let's see. We have f of x, which is x cubed minus 3x plus 2. So first derivative of this is 3x squared minus 3. We analyze this. And we have which means that thing right here. That is true as well. And so we draw this line. We have minus 1, 0, 1. And we know in plus and minus 1, we have these relative extreme points. Or maybe not. We will see. If x is more than minus 1, this function grows. If x is between minus 1 and 1, it decreases. And from here, it continues growing. Now, in order to see what these two inflection points may be, we need the second derivative. That is 6x. And from here, we notice f second of minus 1 is smaller than 0. And f second of 1 is greater than 0. So local maximum, local minimum. Now, with all this information, we can start sketching the graph of our function. We need some more information, namely f of minus 1 is minus 1 plus 3 and plus 2, which is 4. And f of 1 is 1 minus 3 plus 2, which is 0. So more or less, that's our function. Questions? All right, then moving on. Now, for next one, we are going to do something that I know you guys love, and that's involve trigonometrics in this problem. It's number 29. Much better. Yep. And we have f of x is x minus 2 sine x. Okay. So first of all, the first derivative of this is 1 minus 2 cosine x. So we use the first derivative to find possible local extreme values. F prime of x equals 0 if and only if this is 0, so this is 1, so this is 1/2. So x is pi over 6, which is 30 degrees, plus k pi. For k being an entire number. So we have a full family of possible local extreme points. That's interesting. Okay. The decreasing intervals, I'm actually going to save you this part. No, I'm not going to save you that part. Now, what does this mean? This means the number of laps that we do is actually going to change. Moreover, this is not true. Now, what I mean with this, if you go to the goniometric circle, sorry, you have this angle p over 6, and you have minus p over 6, and this is yeah, sorry. My mistake. You have this angle pi thirds, and you have this other angle, which is minus pi thirds. This is the cosine. And so this angle has cosine 1/2, and this angle plus any arbitrary number of laps also has cosine 1/2. However, minus pi thirds also. So you have to consider both. There, much better. Actually, I don't need the minus. So here we are doing an arbitrary amount of laps. We are considering both angles and the possibility to revolve several times. So here, obviously, we have an issue. What exactly does this mean? Well, it means this angle is between minus pi thirds and pi thirds. And I don't know if this goes in camera, right? So this is not true, right? It's not true, indeed. So x is between pi thirds and is this right or wrong? I hate spoiling you the good parts, but this is actually wrong. This is the range of all these angles who have cosine smaller than 1/2. So those are the increasing intervals. We're going to see the decreasing intervals as well. And here x belongs to minus pi thirds plus 2k pi plus pi thirds plus 2k pi. Good. So now we know when the function goes up, when the function goes down, and more importantly, where the inclination changes. So if you come here, we have 0 minus pi thirds plus pi thirds. This may look a little bit confusing. It actually does. And so we have relative extreme points here. How do we say in this function? Is decreasing here, then it increases, and so on. So now we have a very good idea of when the function increases, decreases, and so on, so we can actually check our result with the second derivative. Now, we put any of our candidates here and see what happens. So, first of all, the sine of pi thirds plus 2k pi is exactly equal to the sine of pi thirds, and that is a square root of 3 over 2, which is greater than 0. So all these points are minimums. And here we have the sine of minus pi thirds plus 2k pi, which is the sine of minus pi thirds. This is equal to minus the square root of 3 over 2 smaller than 0. So these are all maximums. Now, let's sketch the function. I'm going to delete this part over here. So between minus pi thirds and pi thirds, we know that this function decreases. So the image will be something over here, and the image of this will be something over there. So the function is something like this. Now, you may be wondering, but there is an inflection point here. There absolutely is an inflection point here. Second derivative is the sign. This equals 0 happens here, so we have a change of concavity and convexity here. If you look here, this region is concave, this region is convex, or the other way around. There is actually no consensus on when a function is concave, when a function is convex. So what I use is if you throw a line through 2 points, if that line is under the function, it is convex. If it's over the function, it is concave. Again, it depends. If you go to a manual specialized in physics, for example, you might find 2 or 3 different concepts of concavity and convexity, and they basically use them to convenience. So just make sure to stick to only one definition and use that all the time. That way you will be mostly right no matter what. So, oh, this is a funny one. I'm going to show you one more before the break. And that's number 37. And we have our candidate function of the day, This f of x is the absolute value of x squared minus 1. Okay, so to begin with, this function doesn't have to be derivable in any point. So let's see where this function is defined by pieces in this way. So we have to analyze this piecewise. Very important. So first of all, and that's it. Functions with absolute value are not derivable in points where they change sign. Let me show you why. Imagine we have here the function y equals absolute value of x. We try to find this function in 0. And I'm going to do a trick here. So we have a function h, and what I'm telling you is that I'm defining the derivative as the limit of the derivative when this thing tends to 0. What is going to happen is that when we define our distance h here, there is actually no way that works, because the function is defined differently here, and so the thing is not going to work. So I'm going to call this k instead of h. And so this is the limit when h tends to 0 of the limit when h tends to 0 of f of minus k halves plus h minus f of minus k seconds divided by h. This is f prime and let's see what happens here. So what we have here is what happens here is that we have this, which is positive, so we can leave it like that, minus this thing, which is negative and has to become positive. Sorry, the other way around. It has to become positive, so minus plus, is this working? and this limit is equal to 1. So we have to find the derivative in some little enclosure that contains 0. So when we make k tend to a's that tend to 0, this is going to tend to 0. And what we get is that the definition of the derivative becomes 1. So this limit kind of here becomes 1, and that's a big problem. That's really a big problem. Do you want to know why? Because if we take minus 8 instead of plus 8, and we replace everything, here we get minus 1. So the derivative coming from the limit that defines the derivative coming from one side, and the limit that defines the derivative coming from the other side are different, which means the limit at the point is not defined. So these peak points have no derivative. This may have been a little bit more messy than it should, but I think it's important for you guys to know if you have peaks in your function, the function is not derivable in those points. So there is no derivative to this function. Now, let's see what happens with the growth and ungrowth intervals. This is 0, this is minus 1, this is 1. Here we can observe it immediately. If we are in smaller values than minus 1, this is negative. Between minus 1 and 1, it's minus 2x. So if we are moving in negative amounts, this is positive. If we are moving in positive amounts, this thing is negative. And it's positive if x greater or equal than 1. Consider here that in 0, the derivative is 0. So we have an inflection point here. I mean, we have a local extreme. So we observe another thing, and it's that f of x is always greater than 0. So we have two local minimums, which are absolute minimums, and a local maximum. In order to check that 0 is a local maximum, I'm going to take a look at the second derivative, which is 2 if x squared greater than 1, minus 2 if x squared smaller than 1. So x0 is a local max. Second derivative is smaller than 0. It's a maximum. So we have the intervals of increasing and decreasing. Now we can draw the function, because we know what happens in this point. So in this point, this is 1 as well. The function is decreasing, but it's always positive, so it comes from the infinite doing something like this. It has a peak here, but here the tangent is horizontal. So the function does something like this. It goes down again, and it goes up again. So this is your function. Remember, you can't derivate the peaks. So you have to treat them as x equals minus 1 r Absolute minimums. Peaks are a little bit of an annoyance sometimes, but you can work around them, no problem. And with this, I see that is 10 past. So I'm gonna call this a break. We'll be back in 10 minutes. If you don't have questions about this part, obviously. Much better. All right. Is this function concave or convex? It's both. Now, if it's both concave or convex, how many inflection points does this function have? Infinite, not exactly infinite. Which infinite? The infinite of natural numbers, the infinite of real numbers, the infinite of vectors in space. Does it have one inflection point? Does it have more? The answer is all. All points of this function are inflection points. So if you ever get asked, or you are just trying to win a bet or something like that, hey, I bet you $500 I can build a function with infinite inflection points. Easy money. Now, ooh, I found one that I'm going to have you solve tomorrow so badly. so badly. At first, (4.5.37) if f is concave. Its graph, it's always tangents. Is there a reason to introduce convexity when talking about straight lines? Of course, there's a reason to introduce convexity when talking about straight lines. Straight lines are actually curves. They are, by definition, the curve that is neither concave or convex or both. Depends on how strict your definition of concavity and convexity is, but it's at both times, neither and both. It's not only there, it's fundamental. Now, if f is concave, its graph it's above its tangents. This is what we mean with this, okay? Now, who agrees with this statement? Who doesn't agree? Who has an idea on how to solve this? No ideas. All right. Then let's do this. So this is a number, this is a number, and this is a number. Now, this doesn't necessarily look amazing, but if you take a close look, this is actually a familiar figure. So let's do some analysis here. This is f prime of x minus f prime of x0. Because, you know, this is a number, and this times this is also a number. so it's not going to matter. And if you look at this, this is 0 if and only if x equal x 0. So we have a local extreme point. Now, second derivative is equal to the second derivative of x. By definition, it's concave. So this is true, which means this thing right here is a local minimum. Of course, this is 0. So h of x is greater or equal than 0 for all x in our interval. Now this means this is starting to look good, right? One more step. Sorry. And we are done, ladies and gentlemen. What did we find here? This is the function. And what is this? This is a straight line that starts in x0, f of x0, has a slope equal to the slope of the real tangent, and it touches the function in the same point. So what is this? This is the function, and this is the tangent at any point. So this is okay, the drawing is terrible, but the idea is there. Now, questions about this. Just for the record, I had to do this exercise in an exam, the first year of my bachelor. I didn't do it exactly this way, but this is actually way more practical. So yeah, if a function is above the tangent, it's concave. If it's below the tangent, it is convex. Fair enough. Okay, I see exercises in section 4.6 are mostly about drawing. So we're going to do one, and then there's time for questions. That question is 4620 something. Y squared in power x. This is exercise 34. So the idea is we want to sketch this function. We have absolutely no idea what it does besides one thing. This is positive, this is positive. So we have nothing below the x-axis. So let's see. First of all, this is the first derivative. And second derivative. Is something like this. Derivating things that are multiplied by e in power x is very simple. It's this thing plus its derivative, and everything multiplies e in power x. So let's talk about increasing and decreasing. So this is greater than 0. Oh, sorry, this is equal to 0 if and only if this is equal to 0. So we have 2 points. One is 0 and the other is -2. So there are two points of not growth. Now, let's examine the signs this way. If x is smaller than -2, this is negative, this is negative. If x is between -2 and 0, what happens if this is between -2 and 0? Let's take x equal -1. Then this is 1, -2 is more than 0. This is more than 0 as well. And if x is greater than 0, both of those things are positive. So this is positive. So this already gives us an idea. This is not a local extreme. This is probably an inflection point where the function does something like that. Let's see. Now we're going to examine the second derivative. This is x squared plus 4x plus 2 equals 0. So x is -4 plus minus square root 16 minus 8 divided by 2. This is -4 plus minus 2 square root of 2 divided by 2 minus 2 plus minus square root of 2. Okay. So you have 2 points where concavity and convexity changes. I'm going to note it down here. 0, -2, -2 plus square root of 2, -2 minus square root of 2. The second derivative, if x is smaller than -2 minus a square root of 2, let's pick up, for example, x equal -3. This polynomial is 9 minus 12 and plus 2, which is more than 0. Between these two roots, we can pick up, for example, -2. This is 4. This is -8. This is 2. So this is more than 0. And on the other side, we can pick up, for example, 0. This is greater than 0. You may be wondering, why do we need derivatives to be continuous? Well, if they are continuous, we can do things like this. Like if they cut the axis in one point, the sign of it is constant at each side. So we have that thing. So we know that we have 2 inflection points. Did I do this correctly? Okay. All right. So in -2, we know that the second derivative is smaller than 0. So x equal -2 is a local max. Which is absolutely not to be mistaken with the place where we should go to have dinner after the exam. So we are already kind of in a position to talk about this function. Let's draw the x-axis a little bit lower. This is 0. This is -2. This is -2 plus a square root of 2. This is -2 minus a square root of 2. And now f of -2 is 4 in power -4, which is somewhere here. Here would be so the function comes like this with a certain convexity. Here it has an inflection point, so it changes the concavity and convexity. Here we have another change. So this goes something like this. And from here, it just goes up very fast because it's square times exponential. So this is more or less what the function looks like. It looks pretty weird. these kind of things happen all the time. Now, questions about this function over here. First of all, you may be wondering, we have said that this function is decreasing. So why does it increase here? Something like that. It looks simple at the beginning, didn't it? Like with this. It kind of looked a little bit too good to be true. Happens all the time. Now, let's move on. Okay. So to wrap it up, I'm gonna show you how to solve another second order linear differential equations. I think we didn't solve this one. Hopefully. So, first thing when solving a second order ODE is characteristic polynomial or characteristic equation. I generally call it polynomial for the reasons I gave you the other day. Have a lambda squared plus 4 lambda plus 5 equals 0. And from here, the eigenvalues are minus 4 plus minus the square root of 16 minus 20 divided by 2, which is minus 2 plus minus 2i. Okay, we have a problem here. We have complex eigenvalues, which now that I think you're not seeing because they are out of sight. So, if we have complex eigenvalues and they are conjugate, our general solution is y is a e in power the entire part times t that multiplies, if I remember correctly, b cosine the imaginary part t plus c sine of the imaginary part. This is the form, if I remember correctly. I'm gonna check if I remember correctly. This, much better. So the exponent is the real part. The argument of the cosine or sine are the imaginary part with positive sign. If you were to consider negative sign, you would have to change sign in this constant, but that's not really relevant whatsoever. So now we want to determine the constants. Because you may or may not have noticed, but we have an infinite family of functions, one of which is the solution. So first of all, we have y of 0 equals 2. So 2 is all this, which is 1, times b cosine of 0, which is 1, plus c sine of 0, which is 0. So b equals 2. Now we have to derivate that. Now y prime is minus 2 in power minus 2t 2 cosine of 2t plus c sine of 2t plus in power minus 2t that multiplies the derivative of all of this, which is minus 4 sine of 2t plus 2c cosine of 2t. Now, derivative of a product, nothing new under the sun. And now we use the second condition. And let's see what happens. This is 1. 2 cosine of 0. 2. C sine of 0. 0. Plus 1. That multiplies. Minus 4 sine of 0. 2c cosine of 0. This is minus 4 plus 2c. So the equation is 2 is minus 4 plus 2c, from which 2c equals 6, c equals 3, second constant, first constant, and so the solution is the one curve in the infinite family defined by okay, this was pretty straightforward. Now you have 4 minutes worth of questions. how did I get 2 equals 1 times b plus 0? We use the first condition, y of 0 equals 2, and we substitute it here. Y equals 2, and we go here to our general equation, and we substitute t equals 0. Here we have e in power minus 2 times 0, which is 1, b times cosine of 0, which is b times 1, b, plus c sine of 0, which is 0. So we substitute everything, b and 0. And so when you put all this together, you have 2 equals b. So that equation has solved itself. All right. If there are no more questions, then I'm going to call this a day.